All right, we have just finished the first two learning objectives, so now we can talk about higher order derivatives of functions. Here we go. Uh, in the previous section, we just learned that velocity function is the derivative of the position function, which is the rate of change of displacement in time. So now if you take the derivative of the velocity, which is the rate of change of velocity in time, you get acceleration. And since the acceleration is the derivative of the velocity function and the velocity is the derivative of the position function, so we can look at acceleration as the second derivative of the position function, and we're going to use a notation for that. So calling s of t to be the position of the a moving object. The first derivative we denote it by s prime of t is the velocity function, so we're going to use v of t to denote the velocity. And the derivative of the velocity, which is the second derivative of the position function, is what we called acceleration. And we're going to use the double prime notation to represent the second order derivative. Going parallel with this example, we can also talk about higher order derivatives, like the third, fourth, fifth derivatives of functions. And in fact, we're going to use different, well, we have already used different notations to represent the derivatives, but we're going to see like how we can represent higher order derivatives in terms of their notations. So for the first derivative, remember that we use the prime notation. So if you put 1 prime as a superscript, we know that you're talking about dy over dx. In other words, the derivative of y with respect to the independent variable x. And for the second derivative, you can use the prime notation again. This time you're going to put 2 primes. For the third derivative, it's going to be 3 primes. But after the third derivative, you can't put so many primes because of the space problem. So what we do is, like, to represent the derivative starting from the fourth, we use the number 4, 5, 6. We use the number corresponding to the order of the derivative, but in parentheses. So when we have like y superscript 4 in parentheses, we are going to take it as like the fourth derivative of the function. And for the nth derivative of the function, y is going to be represented by y superscript n. Now let's see how this works in other notations. So we have f prime, f double prime, f triple prime. Nothing changes so far, but starting from the fourth derivative, we're going to use the superscript 4 in parentheses and n in parentheses for the nth derivative. So pretty much these two are almost the same. What makes things different is starting with this concept here that we use this notation dy over dx. So this is representing the first derivative. So when you come to the second derivative, you put the 2 as a superscript for d, and you read it like this: d squared y over dx squared. So we also put 2 here, so we will take it as like we're talking about the second derivative. For the third derivative, we put 3 here and 3 here, 4 here and 4 here, n here and n here. Okay, so out of the first 3 notations, I think this is very commonly used, and you will see this type of notation popping everywhere. And if you want to use the ddx type notation, well, again, y is replaced essentially by f of x, and we use the bracket notation. And the same thing here. See, all the y's here are changed to f of x, and we keep just the rest: d cubed over dx cubed f, d to the fourth divided by dx to the fourth, f of x. So we will see that this is the fourth derivative, this is the nth derivative. You can also use the operator notation. So when I say d sub x y, it's essentially y prime or dy over dx. D sub x squared y is the second derivative, d sub x cubed is the third, and d sub x to the n is the nth derivative of the function. So I would just get familiar with all notations, all types of notations here, because in certain questions you will see that the question is asking the fourth derivative in this form or in this form, so you will know what you are talking about. Here is a good application problem where we have a falling object on the surface of the moon following this position function formula. Essentially, it doesn't matter if you go with a feather or a hammer, so you will have the falling object following the same formula. And here S is the height in meters and T is time in seconds. And the question is asking, like, what is the ratio of Earth's gravitational force to the moon's? Okay, so first of all, we got to find the acceleration on the moon, which is the second derivative of the position function. So let's try to take the derivative of the position function twice. And we're going to use the power rule for differentiation. So we're going to put the 2 down and subtract 1 from the power for the t squared term. And for this term 2 here, the derivative is going to be 0. So the first derivative yields negative 1.62t. And if you take the derivative of a negative 1.62t one more time by using the power rule, you get down to negative 1.62, which is the acceleration function. And that is, in fact, the gravity on the moon, the acceleration due to the gravity on the moon. So it's meters per second squared. That's the unit of the acceleration due to gravity on the moon. And we know that on Earth, it's like 9.8 meters per second square. So the ratio of the Earth's gravitational force to the moon's would be 9.8 divided by 1.62. And this ratio takes you to approximately 6.0. So which essentially means that on Earth, the objects fall almost six times faster. All right, we're done with the last learning objective. We talked about the fact that the derivative of the position function is the velocity function, and the derivative of the velocity function is the acceleration function. So this takes you to higher order derivative concept. You can even talk about third, fourth derivatives of position functions or other functions. So please go ahead and start watching the recitation videos, and once you're done, and you can perfectly start the homework assignment corresponding to this section. So thanks for watching. I'll see you in another video. Bye.